Class 17.1, we'll be going over rigid body kinetics. Rigid body kinetics has two equations. One's the base equation that we've been working with for the longest. Force is equal to mass times acceleration. On this time, it is the acceleration of the center of gravity. The second equation, which is given because not only are rigid bodies moving in a straight line, but they also rotate. This helps with the rotational motion. The moment of the inertia is equal to the mass moment of inertia plus the parallel axis theorem multiplied by the angular acceleration of alpha. To get the moment of inertia is equal to r times f. If you come right over here, r is equal to the distance of your O multiplied by your force. With me, it helps if you draw a straight line from O. This point right here would be O. You draw a straight line and go all the way down, and you just connect that to to your center of gravity, and that's how I find my R. To get the IO, the inertia of O, the mass moment of inertia is always given in the back of the book. You add that to your parallel axis theorem. Parallel axis theorem is simply your center of gravity with a straight line drawn through it. You find your O, straight line drawn through it. That's how you get the parallel, as you can see, and it's just the distance in between. As we said already, the inertia is given in the back of the book, and it's simply your inertia of the center of gravity plus your mass plus your time multiplied by your distance squared.
This is chapter 17.2 deals with planar kinetic equations of motion. Over here you have the two major points of planar kinetic equations of motion. You have equations of translation in motion and equations of rotational motion. Equations of rotational motion deal with bodies moving in a circular path, and translational motion deals with particles moving in a uniform manner. This is a representation of forces acting on the body, and it's due to the gravity. Force of sum of the forces equal to the mass times the acceleration due to the center of gravity. This can also be broken down into two components of x and y. Second, rotational motion deals with the two forces, Fi and small f of I. F of I, the big F of I, deals with the resultant external forces, and the small one deals with the resultant internal. Mg equals the inertia times gravity of the angular motion. And the rule of this is to always draw your free body diagrams.
Alright, 17.3 is about translations. And like John said, the first thing you always do is draw your free body diagram. And with that, we have F equals MA. And with 17.3 is talking about translations. You have two translations. You have rectilinear translation and curvilinear. In rectilinear translations, in your free body diagram, you have your forces on one side, and you have G, and you have a point which is a part of the A. And it's always, A will be always parallel to G. And right here, you have your distance and your moment equations. Fx equals mag in the x direction, and Fy equals mag in the y direction. And your moment equation is ma, summation of ma equals mag times d, your distance. In curvilinear translations, you have your forces, you have G, and the translation for curvilinear is your curvilinear line always passes through G, and with curvilinear translation, you have to take in your tangential and your normal directions. And here you have, to stay parallel to the curvilinear translation, you have the distance E and H, and that'll always give you a parallel. And your summations would be F of N, which is normal, equals mag times N, and F of T, which is tangential, equals mag times T. And your moment equation would be MB equals E times your moment tangential minus H times your moment normal. And that wraps up 17.1 through 17.3.